Good afternoon, and welcome to Energy Storage for a Changing World. I'm Linda Young, an Argonne Distinguished Fellow, Group Leader in the Chemical Sciences and Engineering Division, and Committee Chair for the Director's Special Colloquium Series. Before we start, let me explain how we will manage this meeting. BlueJeans works best in the Chrome browser, so if you've connected using another browser, you may want to exit and reconnect to Chrome. Your video and audio were automatically turned off when you joined the meeting. If you have questions related to the technology of this meeting, for example, if you can't hear the presenter or see the slide deck, use the Moderator Chat feature and we will help you troubleshoot. This private chat may be accessed by clicking the icon that looks like a talk bubble. The public chat has been disabled for this event. To ask questions throughout the meeting, please use the Q&A function, which is in the square icon labeled Q&A. In this feature, you can pose new questions or upvote questions asked by other attendees. By upvoting or liking a question, those moderating the questions will be able to see which are most popular or of the most interest to those listening to the presentation. We have, however, added the ability to turn on closed captioning for the event. In the lower left side of your screen is a button with a blue outline that is labeled CC. Click on that button and three moving dots will appear on the bottom center of your screen. That's where the closed captioning will appear. Turn it off, click the blue CC button again. Please note, this is only available if you've logged on with your computer and not if you have joined via cell phone. The closed captioning is computer generated, so may not display names and other words correctly. Last, please note that this session is being recorded and may be posted for viewing at a later time. By participating in this session, attendees consent to being recorded. Now, it's my pleasure to introduce Laboratory Director Paul Kearns. Dr. Kearns has been Argonne's director since 2017. He has set the laboratory's strategic vision to deliver pivotal discoveries, pioneering leadership, and powerful scientific tools and facilities. And now, here's Director Kearns.
Thank you very much, Linda. Welcome, everyone, to the first Director Special Colloquium of our 75th anniversary year. Energy Storage for a Changing World. I'm Paul Kearns, and I have the honor of serving as Director of Argonne National Laboratory. As you know, our lab is dedicated to leadership in science and technology. And our guest today, the 2019 Nobel Prize winner in chemistry, is emblematic of that idea. Stan Whittingham's participation in this event is very special for Argonne, which has a long-standing energy storage program going back many decades, supported by multiple offices in the Department of Energy. Argonne's research and development and energy storage spans the short and long term to ensure we have a full pipeline of technology innovations. In the short term, we are focused on advancements in lithium ion batteries to enable the rapid electrification of light-duty vehicles by solving issues related to cost, safety, charge times, and the abundance of raw materials. In the longer term, we are building batteries from the bottom up for a broad range of energy storage applications, including long-duration storage for the energy grid and beyond lithium-ion chemistries through the Joint Center for Energy Storage Research, or JCESR. With the new administration in Washington, D.C., there is a refocus on climate change solutions, ambitious goal of getting the U.S. economy on course to achieve net zero emissions by 2050. With expertise across the energy storage value chain, from discovery of materials to development of new battery systems for the electric grid and testing, all the way to recycling through our resale center, Argonne can help. And with JCESR, we continue to lead collaborations that innovate advanced battery technologies beyond lithium ion to help achieve the needed decarbonization by the middle of the 21st century. But Argonne's work and the efforts of everyone else in the energy storage field would not be possible without today's keynote speaker. Stan Whittingham was instrumental in the development of lithium-ion batteries, which are currently used in everything from electric vehicles to laptops to the very cell phone in your pocket. They have revolutionized everyday life, and it is difficult to remember a world that did not have these batteries. To those old enough, or not old enough, I should say, to those not old enough to remember, such a world did not in fact exist in the 1970s. That was when Stan discovered intercalation electrodes and described the concept of intercalation reaction for a rechargeable battery. Near the end of that decade, he patented the first rechargeable lithium-ion battery. His invention, like many others before, laid the foundation for subsequent innovations. His discovery literally powers the modern world as we know it. From the development of lithium-ion batteries, awarded the Nobel Prize in Chemistry, along Akira Yoshino and John Goodenough in 2019. The concepts he formulated continue to enable breakthroughs in cutting-edge innovations, technology that is crucial to confront climate change. For these and many other reasons, we are so eager to Dan tell us about his work and its implications. After his address, we'll have a Q&A followed by a short video clip, and then we have a panel discussion with Stan, George Crabtree, the director of JCESR, and two other accomplished energy leaders. Melanie Kenderdine, the principal of the Energy Futures Initiative, and Mary Powell, former CEO of Green Mountain Power, Vermont. I'm looking forward to the timely and engaging discussion our panel will have on the integral role that energy storage technologies will play in ensuring our nation is on a path towards a decarbonized economy. Thank you, everyone, for attending today's Director's Special Colloquium. We're grateful for all the hard work of our colleagues and the strong support of you, the public, and our sponsors. Your support helps Argonne accelerate the science and technology that drive U.S. prosperity and security. Together, we are unlocking new frontiers in technology, securing America's energy future. It's now my honor to introduce Nobel laureate Stan Whittingham. Stan, please.
Okay, I'm there. Thank you very much, Paul. And what I'd like to do today is discuss lithium-ion batteries starting from the beginning and explain how they've changed and really what they can do today and our duty really to use them to help out the world. I would like to thank Department of Energy first, who supported my research for almost 30 years now, and particularly Jen, Dave, and Craig who are supporting it today. So what I plan to do today, just give you a rough idea, start in about 72, come up to the present time, show how we had an idea and how it's come to dominate, then show potential impact on the environment, and then discuss some of the limitations, and then discuss some scientific opportunities. And if there's any DOE folks listening or politicians listening, give a pitch that it's now our turn to pick up the ball. We dropped it back in the 80s, but maybe we can take it up again. But first, let me thank what was then ESSO, who initiated lithium rechargeable batteries. And I should also thank somebody, some of you may well know, my boss at Exxon for many years in corporate research and engineering was Al Schriesheim. And Al was director of Argonne for many years. And he was a champion of what we're trying to do at Exxon and encouraged us throughout. So let me show you what the kind of things we were working on. We're working on titanium disulfide. We use basically large single crystals as shown here. And if you've been reading the latest literature on the oxides, people are going back to single crystals. They have an advantage of having a lower surface area, less cracking, and less side reactions. But what we did do at Exxon is make some smaller batteries. This one shown at the top right has a lithium battery in it, a little clock, and a solar cell. And we gave this away to potential customers. It was basically a paperweight. This particular one still sits on my desk here, and it was built, I think, about 1975. So it's about 45 years old. It's still working very well. And I should point out that folks at Rutgers helped us test these cells about 3-4 years ago. They tested some of the old cells from the 70s, and they still had about 70% of their original capacity in them. The well-made lithium-ion batteries I won't say last forever, but they'll last for a very long time. Below that are some large cells. These are about 6 inches by 4 inches, about an inch thick, that we displayed at the EV show in Chicago in 1977. They turned the motorcycle headlamp on and off all week long with no problems at all. You'll notice on the top they have a pressure release valves, and that was because we're using some boride salts in ether solvents, and we're afraid of any pressure buildup, so we tend to release the pressure at nighttime. Now, remember that little cell? If you want to see that again, you can find that now in Stockholm. 2 cells we have here. Here's the one I just showed you, or a copy of it. And here's a button cell. And here's the Exxon brochure, which was actually batteries were part of a separate division called Exxon Enterprises. And this was the technical brochure given away to potential customers. So I'd say these batteries essentially last forever. There's really no problem with them, but you could never make batteries this well today because these were welded closed with glass seals. So let's look at where they've come from those first early days. And I show you a series of, let's start with the vehicles here. Here's a 2-seater electric vehicle that my wife and I rented in Bermuda almost 2 years ago now for our 50th anniversary. And it had been on the island maybe for 2 weeks. Tourists are not allowed to drive cars. You're supposed to drive scooters. But they passed a new law allowing tourists to rent these small electric vehicles. And they don't go very far, so you can see we had to recharge it. But they are, I think, much safer than scooters. In contrast, to the right of that are 2 large trucks. This is a 16-wheeler. At Peterbilt, at their PACCOR test facility in upstate Washington. And here's a garbage truck, almost perfect application for batteries because it stops, start, up and down. And I was lucky to get a chance of driving both these around their test track. Another place where electric vehicles are commercial now is in Germany, and this is a Mercedes bus that presently has lithium-ion batteries in it. But as at the end of this year, early next year, it will have a solid-state battery option. And I'll talk more about that a little later. The other area where obviously batteries are very, very important is the whole area of renewable energy. If we don't use the sun or the wind, we need storage. Both these are intermittent, but both are a clean environment. And again, I'll talk more about these in a moment. And clearly, energy storage enabled the communications revolution. And it's really the smartphones or the toys that came before them that were the alpha tests of lithium-ion batteries. Almost no lithium-ion batteries are tested by industry long-term. There is not enough time. So it's us, the consumer, that does the alpha testing, beta testing, and hopefully nothing goes wrong. Let me show you another application where lithium-ion batteries is now dominant, and that's out in space. So I and 2 of the physics laureates in December of 2019 were lucky enough to speak live to the International Space Station and talk to these 2 astronauts. The lady is from the state of Maine. Her mother is Swedish, hence the 2 flags. And the fellow is from Italy. And they were busy at that time just completing the replacement of all the nickel metal hydride batteries that store the solar energy with lithium-ion batteries. And they were very pleased because lithium-ion batteries weighed half as much, took up half the space, and were anticipated to last twice as long. And if any of you read the comments from the Nobel group in Stockholm, they made the point that really lithium batteries, besides the wireless revolution, will allow a fossil fuel-free society. So this is where we really need to push. And a number of us back last May wrote an editorial in support of not going back to the normal. We've got the opportunity, if we invest after the virus goes, to invest in clean energy. And I'll show you in a few slides that that investment makes a lot of sense. So let's just look at what's happening right now. Electricity from renewable energy needs storage. Today, without any subsidies, renewable has a lower cost than new coal. And this is probably best exemplified by Texas. So obviously in the last few days there's been some hiccups there. That as of last August, the planned connection of new power sources to the grid was 94% renewable. This is solar plus wind plus storage, little bit of gas, essentially no coal and no nuclear. So even here in I would say, a climate unfriendly state, renewables are taking over. And I think utilities are seeing the huge advantage of renewables. Once built, there's essentially no cost during operation. The fuel is free, you don't have to ship it. You just have to worry about whether the sun or the wind blows. But if we now look at the status of storage, this has changed dramatically in the last 12 months. I think 12 months ago, Tesla had the largest storage facility in South Australia. Then the one in San Diego beat it by a few megawatt hours. But last December, the picture I showed you here is a 1.2 gigawatt hour lithium ion facility at Moss Landing in California. And this used to be a gas-fired power plant. They took all the gas-fired system out, put in batteries, but all the essentials of the grid are there. So all the transformers, everything else you need. So this is almost an ideal situation. It's planned that this will expand to 1.6 gigawatt hours this year, and they've got approval from the local authorities for an eventual expansion to 6 gigawatt hours. So lithium ion is viable, extremely large scale. And at the end of my presentation, I'd like to briefly discuss the actual chemistry being used in these, because some of it does not make sense to me. These are, as I understand, all using oxide cathodes. So let's briefly look at a little bit of the history of the lithium batteries. And I don't really need to go through, I think, detail on this. Every battery has an anode, a cathode, and an electrolyte in between it. And around about 1970, there were essentially no indications of lithium rechargeable batteries. But no, there were several at that time, lithium primary batteries, particularly in Japan, for fishing floats and other devices. Exxon wanted to be an energy company, and Exxon was interested at that time in building electric vehicles, not just the batteries. So we embarked on a battery program. It initially used lithium metal. When we went commercial, we had switched over to lithium aluminum because we had already recognized that dendrites cause problems, particularly with the electrolytes we used. Lithium aluminum only cycles satisfactorily for less than 100 times, so that had to be changed. And there was really Akira Yoshino in Japan who showed that carbon, and he initially looked at polyacetylene, could store lithium, and those graphitic carbons that are still used today for lithium-ion batteries. And it was Sony who picked up that technology, launched it, and were really the first ones to make money off lithium-ion batteries. Exxon had tried, Molly Energy had tried, but not made money. The big challenge there, though, is that you need 72 grams of carbon to store 7 grams of lithium. So if you want to increase the energy density, we have to change the anode. And present day, and I'll show you in a moment, people are going back to lithium as an intermediate. Silicon may be the way to go. On the cathode side, we started on lithium titanium disulfide, and I'll show you why in the next slide. John Goodenough, who was at Oxford at the time, was studying the magnetic behavior of lithium cobalt oxide. and he noticed the similarity of the two crystal structures and decided to test it in batteries. And we all know the results of that. Obviously, cobalt is too expensive and has child labor issues. So for large-scale commercial applications, most of the cobalt is gone, and we now use a mixture of nickel, manganese, and cobalt, or as Tesla does, uses nickel, cobalt, and aluminum. Again, I'll get into that in a moment. John, a few years later, found out the olivine lithium ion phosphate was reversible, and again, this is a naturally occurring mineral, and for a while, this was a very active cathode material. It's not so active today, but I think it will come back. And because it's much lower energy density, carrying that phosphate group around, we decide it'd be a good thing to look at, can we stuff 2 lithium ions in there or 2 sodium ions in there, and to increase the energy density. So let's go and look at TiS2, what was special about it, and why it's still of interest today. So on the left-hand side, you'll see we have a plot of the discharge curve of a lithium titanium disulfide cell. This is the 76th cycle. It's at 10 milliamps per square centimeter. This is probably higher than we run any lithium-ion battery today, and it's at room temperature. And I should note it has no carbon black or any other material in the cathode, just a little bit of binder and pure TiS2, because it is essentially a metallic conductor. So every point of contact of the liquid with the TiS2 can react. A number of groups, including Brian Steele in London, looked at sodium. And you can see the sodium diagram is much more complicated. That's because you actually have to expand the lattice, get the first sodium in. So you've got a series of single and two-phase regions, which makes it harder to use in the battery, and you lose energy from the nucleation processes. Then on the right-hand side is a magnesium cell. This is work of Linda Nazar at Waterloo, done under the auspices of JCESR, that's George's group. And this is the best data, as far as I know, at this time, showing the cycling of magnesium ions. So again, TiS2 is a metallic conductor, so the electrostatic repulsions are substantially minimized by the electrons on the TiS2. And you can see she got more than 40 cycles out of this at essentially 100% Coulombic efficiency. So TiS2 still remains, I would say, a model compound. A number of people working on lithium sulfur cells are using titanium disulfide or vanadium disulfide as a substrate for the sulfur. And it's good in the sense it's also electrochemically active, so you're not throwing away energy there. So let's look at where we stand today. We look at today's intercalation batteries. A lot of people say, well, you got the Nobel Prize, everything's finished, right? It couldn't be further from the truth. So just worry about what's inside that red circle. Today, on a volumetric basis, we're only getting somewhere between 11% and 25% of the theoretical energy. So there's a huge gap there which we can fill. On a weight basis, the right-hand column, that's the same thing. And you can see it's around about 25%. So I'm part of the Battery 500 consortium, and our goal is to get that number up to 50% or 500 watt-hours per kilogram. To do that, we've got to get rid of most of the carbon anode. As I said, that takes up half the volume. We've got to use all the lithium that's in the layered oxides, which we don't today, and I'll talk about that in a moment. And we ideally need materials with higher ionic and electronic conductivities. If we had those, then we could use thicker electrodes and reduce the amount of current collector and separator. So let's look at what are the challenges of these layered oxides. So as I mentioned, the lithium cobalt oxide still dominates the electronics. It has the highest density, which means it has the highest energy density per unit volume. And really that's all you care about for your smartphones. but the mixed metal NMCAs are now the dominant materials for essentially all other applications. And clearly, argon played a key role in these layered oxides. They have a number of the patents. And at this point, I might mention that we should all congratulate Mike Thackeray, who played a key role in this and was just a week ago elected a member of the National Academy of Engineering. So what has happened in the NMCAs? There's a huge effort now to eliminate cobalt. It's obviously cost and environmental issues. Vehicles have gone from 30% nickel to 60% nickel to 80% nickel. For some of you who don't know this nomenclature, I showed you at the bottom here. 6 just is the amount of nickel, next one's manganese, next one's cobalt. So right now, solar vehicles are using 80%. I'm not sure how many. It's reported recently that Tesla is now using 90% nickel in their NCA. So everybody's pushing the nickel limit. That is now giving us, I think, a challenge of safety versus energy. And if you look at this famous plot to the right here, this vertical axis is the thermal stability. So the higher you are on this axis, the safer the material. So these layered oxides, you can see the 30% nickel is the safest. But if you want high energy density, high capacity, you have to go to high nickel. This one, the bottom right-hand corner is 85% nickel. Its thermal stability is 100 degrees less than that of the 30%. We hope our batteries never get this hot, but the thermal stability is a direct measure of how reactive they are with the electrolyte. So if we need to reduce the likelihood of these materials generating oxygen, which is then what reacts with our solvent. So in a number of these materials, a little bit of aluminum and magnesium is added. That's where the A comes from in NMCA. This stops you removing all lithium, improves the stability by a few degrees. But ideal would be a manganese-based system. It'd be safer. Manganese is much lower cost than either nickel or cobalt. And clearly, Argonne again has done a lot of work on the lithium manganese rich compounds. And I think you're going to see more and more work done on those compounds as the years go on. So let me just show you how we're doing in our Battery 500 project. And this is one that comes out of EERE in DOE and led by Pacific Northwest National Lab. And Jay Xiao, one of my ex-PhD students, is one's involved deeply in the battery aspects of that. I show you here the meatball morphology of these materials. To get high rates, you need small particle size. But if you had small particle size, you'd have no density, so they wouldn't pack well. So you then had to pack them in a secondary configuration, making these particles sort of 5 to 10 microns across. I won't go into it today, but the big issue of these is as you take more and more lithium out of these materials, the particles shrink in size, and then in this packed configuration, the particles tend to crack. And these cracks are then fresh surface that reacts with the electrolyte. So there's a relatively large push now to go to single crystal materials and try to get those to work. So just to show you where we actually stand on this material, 2017, we had 300 watt-hours per kilogram and about 50 cycles. A year later, we had more than 200 cycles. In 2019, we pushed this up to 350 watt-hours per kilogram and over 250 cycles. And as of last September, we've now got well over 400 cycles at 350 watt-hours per kilogram. And I show you a typical cell on the right-hand side there. These cells are made at the Pacific Northwest National Lab, then tested at Idaho National Lab. So there's independent testing to where they're made. And these cells also have a volumetric energy density of about 700 watt-hours per kilogram. There is a problem with these materials. If we want to go to 400, we have to use all the material. And if you look at what happens in essentially all these layered oxides, you charge them up, you can get about 230 milliamp hours per kilogram per gram, up to 4.4 volts, which is really the stability limit of today's electrolytes. But when you discharge it, you're losing about 30 milliamp hours per gram. And this is just at the C/10 rate. So we have to use this lower voltage material here. This is where the electrolyte is most stable. So we have to recoup this, and then we can get well over 400 watt-hours per kilogram. We now know this is due to low lithium diffusion at high lithium contents, but we believe, following on the data already on, say, the cobalt oxide, that this should be possible. So if you look at the right-hand side, this is 80% nickel. The black curve is room temperature cycling. So you can see we lose all of this material. But if we hold it for 100 hours, we get it all back. Clearly diffusion controlled. If we increase this to 45 degrees centigrade, there's much less of an issue. And this is just going from 21 to 45. So that's a very little temperature change, very little energy in KT. So we should be able to modify the material. If you look beneath that is cobalt oxide, and you can see there's essentially no first cycle loss. So our goal right now is to make our NMCs look more like cobalt oxide as far as its first cycle loss goes. And what we're doing is coating these materials and a bit of substitution. And in this case, we're using niobium. And you can see just using 1% niobium, we've recovered about 50% of that first cycle loss. So with a bit more effort, we believe we can get it all back, in which case we can push these materials more to their limit without actually damaging the electrolyte. A very brief bit of history before I get into the last few slides. So we started out with titanium disulfide. Moderator Energy in British Columbia worked on molybdenum disulfide, that's molybdenite, natural ore there. They built up a fairly large business, but had several fires, so had to back off. And Moderator Energy is still alive, but not doing any pure lithium metal cells. I've already talked about lithium cobalt oxide. Lithium ion phosphate came up next, and I'll show you the tunnel structure of lithium ion phosphate there. And lithium ion phosphate essentially shows no first cycle loss. And behavior on the 500 cycle of lithium ion phosphate essentially the same as on the second or third. But the energy density is low, so not really viable for, should I say, high performance cars. It should be improved if we switch to manganese. That's a 4-volt system as opposed to the 3.5 volt of iron. And we should better further improve it if we can now stick 2 lithiums into the lattice. But with iron, we cannot do it because if we push iron to 4+, then the electrolyte is not stable. So we've been looking at the vanadium analogs. You can go from vanadium 5 to vanadium 4 to vanadium 3. So I wouldn't be mentioning this unless we were successful. And we have indeed shown that it does work. And this was one of the scientists, one of the, I think, only 2 battery activities highlighted by the White House in their February 2019 report. And I show you there one of my students and one of Claire Gray's students in Cambridge picking up the plaque from an Undersecretary of Energy. So let's briefly look at this material. It's a tunnel structure again. So a very stable structure. We make it very easily by what we call a solver thermal process. It's round about 200 degrees centigrade, which is the waste heat temperature of most chem plants and refineries. That heat is essentially free. If we make that material, then we get the structure I've shown you here with protons in it instead of lithiums. If we heat this, we can get all the protons out. And then what we land up with are these little cuboids I've shown you here, about 200 nanometers in size. And if we put a coating of graphene on this, then we get the data I show you on the right-hand side. So we have a plateau about 4 volts. This is vanadium 5 to vanadium 4. Another one for vanadium 4 to vanadium 3. You'll notice lots of bumps in here. This is lithium ordering, which makes this material single-phased in this area, which means it's extremely high rate in that low voltage regime. Not so high rate in the higher voltage regime. And if you look at the black line, which is the first cycle, and the purple line, which is the 50th cycle, you'll see it is in fact better, if anything, on the 50th cycle than on the first cycle. So we've got proof of concept that we can in fact stuff 2 lithium ions into a lattice without damaging that lattice. So we're going to pursue some of the challenges of this material. As I said, we need higher rate in the full voltage regime. We've also got to make it less reactive with the electrolyte. Let me finish by 2 slides, which really raise a few questions we might get into in the discussion. I brought this up earlier. Why are the lower cost and safer phosphates not used more for electrochemical energy storage? The first systems that went in this country, and there's one in Binghamton here, use lithium ion phosphate. The big ones going in now all use oxides, as far as I can tell. So I would anticipate if cost is important, then we should be using phosphates. I said the Binghamton system used cells made by A123. Tesla's now saying they can use lithium ion phosphate for the smaller cars in Asia, which they're shipping to Germany for sale, and they plan to do the same in the US. So the question I think everyone has to answer, is energy density so important? Are the utilities saying energy density is more important than anything else? If that is really the case, this is going to eliminate all non-lithium technologies. I don't believe it should be the case, but we need to understand that. And the other big issue is we need safer, more stable electrolytes. And the question then arises, can solid state give the required power densities? And I show you again this Mercedes bus. This uses lithium PEO, lithium ion phosphate batteries made by Blue Solutions in France. Blue Solutions believe they can get this to work now closer to room temperature. These commercial cells operate about 70 degrees centigrade. They say that in a year or two they'll have it working at room temperature. Only time will tell that. And the other question is, can we go to really all solid state cells using inorganic materials as a solid electrolyte? And can we solve the interfaces, in which case we'll get quite a lot higher energy density? And this is what a lot of people are looking for, certainly in their phones, their laptops, and eventually in most mobile devices. Let me conclude by just saying what I think is probably going to be more important. I've already discussed the first group. In the US, we really need new manufacturing technologies. Today, it takes between 60 and 80 kilowatt hours to produce 1 kilowatt hour of a battery. That has to change. Otherwise, these batteries are not really environmentally friendly, unless we do what the Europeans plan to do, build them using clean hydropower. We need clean recycling technologies. It's not clear to me today that the recycling doesn't also take up a lot of energy. And we really need a regional supply chain and manufacturing. Right now, the components of batteries are shipped around the world before they get in the battery, then the battery is in itself shipped. Europe is a great example of what can be done. They've got plans costing, I think, several $1 billion of their state money, and they're going to be integrated from the mine to the product, which will give clean energy manufacturing. So they're going to make the cathode materials in particular up in Scandinavia and ship those materials to Germany, where the cells will be made to go into the cars. And the question I ask, and a lot of other people ask, is where is in North America's equivalent plant? Surely we can do just as well as Europe, and we need to do just as well. We can't really be held captive by overseas countries. We need to be self-reliant here. And I'll stop there and hand back to George.
So thank you, Stan. That was a wonderful overview with both the past and the future. We're looking forward to the Q&A. And actually, a few questions are already coming in. Let me remind the audience to ask a question. Use the Q&A feature by clicking on the Q&A icon. If you'd like to ask a question that someone has already submitted, then in the Q&A icon, please like the existing question. We'll know that it's important, and that will move it up the priority list. So we'll address as many questions as possible as time allows. And Stan, our first question, you've described the successes of lithium-ion batteries with their proliferation for many applications in transportation and the grid. Is there a possibility of exhausting the world's supply of lithium?
I think DOE, and I'm not sure whether it's your lab, George, did a big study of lithium. And the conclusion was there's ample lithium in the world for all the electric vehicles. And by the time we got half the fleet electrified, we'll start recycling the old ones. So it takes, I guess, about 15 years from when a vehicle is sold to when it is junked. So it's going to take that long. So I don't think there's any issue there. The issue may be if we start building 10, 20 gigawatt hour storage facilities all around the world. But my gut feel is probably enough lithium. If the demand's there, people will look for it. And we didn't know of any lithium in South America when I started in this field in the 70s. If you just Google all the lithium companies in the United States, the headquarters all in North Carolina, because that's where all the lithium spodumene was back in the 70s, and that's where they mined it all. So I think there's plenty enough lithium there. We just have to look for it. The issue will be, will the price start getting higher and higher?
Great answer. Let me ask another transportation-related question. Is there a realistic future in all electric transportation beyond cars and buses, for example, heavy trucks or aviation?
Heavy trucks, I think there's a great deal of interest. I showed you one heavy truck. That particular truck is in the Los Angeles docks. It takes the containers from the ships to the distribution points. So may go through downtowns, so it's clean. Today, the dirtiest, oldest trucks are used for that purpose. There's a lot of discussion, and again, Paco can probably give you more details. The interest is, can you use large trucks, EV trucks, go across the country? And I think there's interest. You could use solar or wind to generate hydrogen on the interstates. Store hydrogen there. Truck will come in, refill with hydrogen. It will still have a very large battery, because fuel cells are pretty useless to acceleration, and they can't really do regenerative braking. So I think you're going to use hybrid vehicles and use the call it waste energy from solar or wind when it's not used so much to actually generate hydrogen at the point of use, because hydrogen is not easily shipped.
Great answer. So building on that a little bit, are there any, so Tesla and Nikola are two companies making long distance trucks. Is anybody making a hybrid truck, as you described, with fuel cells and batteries working in tandem?
I don't know of any in this country doing it. I think there's several in Europe looking at that, but I haven't seen them in this country. And I said the outfit up in Washington State are selling EV trucks now. They're not the Tesla or the other ones where it's promise on the horizon. You can actually go to Peterbilt and get their trucks.
So here's a little bit of a personal question, if you don't mind. The market for EVs, personal EVs, depends on consumer acceptance. And I'm curious if you own an EV or are you planning to buy one?
George, when I retire to a warmer climate where I don't have to plow through a foot of snow or 2 feet of snow, or as in December through 4 feet of snow, maybe. But my wife was thinking of getting a Prius, and she was told not to by the dealer because the road clearance isn't sufficient if you have a lot of snow. So still a challenge in the Northeast, or if you like me, you live on top of a hill. And so I don't have one yet. If I move to California or Arizona, where my daughter and grandchildren are, we would definitely buy one.
Interesting.
There's a reason why they're so popular out west.
Well, most of them are in California, actually.
Yes.
Yeah, interesting. Well, here's another question. You were mentioning you might be able to get to 400 watt-hours per kilogram at the cell level. And I'm curious, let's say you could, what new applications might that enable that we either don't have now or suddenly would be made so much better?
Well, I don't think anybody on this call would complain if their iPhone or laptop computer lasted twice as long. And clearly, the auto companies could make smaller cars if the battery took up less space. Because you look at the cars, they can't really make small ones that would say go 250 miles.
Yeah, that's a real problem, I think. And of course, it would improve every technology we have now, which, as we've all said and you've said, includes a lot of technologies. It's not simply personal electronics anymore. Let me ask you another question. You were talking about putting 2 lithium ions into, let's say, a vanadium unit cell. I don't think you mentioned this, maybe you did. What would the impact on energy density be of that for that particular vanadium phosphate?
It increases the energy density over 1 lithium by about 50 or 60%. So you don't get it doubled because the voltage is reduced.
Yeah.
But the theoretical energy density of those phosphates is essentially the same as the layered metal oxides. It's about a kilowatt hour per kilogram.
It's really an interesting idea. I think looking at the time, we ought to move on. We want to have time for the other speakers and for the panel discussion. First, we have a short video on research in this field, which will be the perfect kickoff for the panel.
The world is in the midst of an energy transition, and you can see this all around. The way we produce, transmit, and use energy has been changing dramatically in the last decade. Electric cars are slowly becoming the reality, but we need much better batteries with longer range, faster charging, and lower cost to make that into something that is mass market. Every time there's a hurricane or some sort of a wildfire, then people immediately start to ask, how are we going to make the grid of the future more resilient? Batteries are at the heart of where we need to get to for the energy transition. Argonne has the largest number of researchers working on energy storage, and we have decades of experience trying to invent new battery materials, but also moving them to the marketplace. So if you think about Argonne's facilities, it ranges from everything from fundamental research all the way to scale up of materials, and ultimately moving those materials from a scaled state to where industry can start to use it. All batteries in the end will reach end of life, and ultimately their capacity will fade. When we do that, we have to start thinking about recycling. And we have a center at Argonne called Resell, where we are working with partners to understand how to cost effectively recycle batteries so that we can start to view these materials as not being thrown away to the landfill, but that can come back into the supply chain. Batteries are all about finding new chemistries and materials associated with those chemistries. So that's the big effort that we're putting at Argonne, is trying to come up with those new materials and chemistries that can have an impact in energy storage and create the future of energy in this country.
Okay, wonderful. I'd like to transition now to the panel discussion. We're going to talk about where energy storage is going, and we're really excited to bring together Mary Powell and Melanie Kenderdine for this discussion. So I will first introduce each panelist, then give them a few minutes for some remarks to get the panel discussion going, and then we'll start with the questions. First is Mary. Mary is a nationally recognized energy visionary and a business owner and entrepreneur. She's the former president and CEO of Green Mountain Power in Vermont. She worked to transform the company by delivering cutting-edge renewable technology for its customers. This not only reduced the carbon output, but also brought down the cost. She also enrolled Green Mountain Power as the first utility in the world to become a certified B Corp for social good. And she partnered with Tesla to become the first utility to offer Tesla Powerwall batteries to their customers. Mary was awarded the PowerGen International Woman of the Year Award in 2014. She won the Burlington Free Press's Vermonter of the Year Award in 2015 and Utility Dive's Executive of the Year in 2019. She now works with her husband on their successful family business, interesting name, Spot the Dog, which sells reflective safety wear for dogs. Mary, the floor is yours.
All right, I will. Okay, so wonderful to be here with all of you today. I just can't begin to tell you how thrilled I am to be a part of this event and a part of, celebrating an organization that has just done such important transformative work in the energy space. And Stan, it was wonderful to hear you. I do have to say, honestly, I think that car dealers are the worst thing for electric vehicles. They talk people out of them more than they don't. So in the for what it's worth category, I will say, as a Vermonter, I've been driving all electric vehicles for a few years now, and they do well in all climates. So I just wanted to put that plug in there, though the range does drop dramatically in the winter, as we all know. But anyway, I really am thrilled to be a part of this event because I really, fundamentally, I love people, I love the planet, and our planet's on fire. Our planet is on fire, and it needs each and every one of us. And I was reflecting, Stan, as I was listening to you, that really what our planet needs is actually exactly what I think we're talking about today, which is the intersection of science, good science that can transform us and move us forward, and love and collaboration. And it really is the combination of those things with a focus on speed, I would say, because we've got to move fast. We've got to move fast to really address the dramatic climate change needs that we have. But it really is those things. It's really about the combination of science, a love of humanity, a love of the planet, and collaborating to get solutions out there. So really, from my perspective, one of the most important topics we could be talking about is the topic of storage. It really, from my perspective, and again, I don't think it's just my perspective. I think we've heard this a lot, that really to address climate change, we've got to electrify everything. We've got to electrify everything. We've got to electrify storage. We've got to create, transportation with storage. We've got to create a more resilient, flexible grid going forward. So when we look at what happened in Texas, I think that is just a great example of, actually, we could have used, I think, a few benefit corporations in Texas as well, because I do think the market and greed do have a bit to do with the mess that we're in. But that said, really to move forward in a more resilient way and to strategically electrify, we really need storage. We need storage in a distributed way so that we can keep communities, homes, businesses online during major climatic events. And we also need storage, again, like what we did in Vermont that I just loved, is it wasn't just about moving towards distributed technologies. It was about moving towards distributed technologies in a way that made the grid more resilient and the grid more affordable. So it was about not just having all of these thousands of homes in Vermont now with Tesla Powerwalls or other storage devices in their home to keep them going during an outage. It was about inventing programs and products and services so that we could create an energy sharing economy. An energy sharing economy where the customers were sharing their storage device with the grid to drive down carbon and drive down cost during the most important times of the year. So it was truly about how do we deploy distributed technologies in a way that not just makes the grid more resilient, more flexible, but really makes it lower cost and lower carbon. And so again, I'm really looking forward to the conversation today. I won't tie us up with a lot more comments than really just to say that we need to move fast. We need to move fast together. We can do this. I fundamentally believe we can address climate change and create a lower carbon, more affordable, resilient grid for all. And storage is the linchpin of it all. So I couldn't be more honored to be with all of you today talking about this very important topic. Thank you so much. Back to you, George.
Thank you, Mary. Wonderful comments, and we'll elaborate on those during the panel discussion. I'd like now to introduce our second panelist. It's Melanie. Melanie Kenderdine founded Energy Futures Initiative along with former Secretary of Energy Ernie Moniz and fellow principal Joseph S. Hazer. It's a nonprofit organization dedicated to driving innovation in energy technology, in policy, and in business models. Previously, Melanie worked in the Obama administration at DOE from 2013 to 2017. She served as both energy counselor to the secretary and as the director of DOE's Office of Energy Policy and Systems Analysis. Before her public service at DOE, Melanie helped establish the MIT Energy Initiative, served there as executive director. And before that, she was vice president of Washington operations for the Gas Technology Institute from 2001 to 2007. During the 1990s, Melanie had her first tour at DOE. She was an appointee in the Clinton administration, where she served in several key posts. She's a graduate of the University of New Mexico, lives in New Mexico and in Hawaii, and is an avid global traveler and an enthusiast of fly fishing. So, Melanie, welcome. Love to hear what you have to tell us.
Great. Thank you so much, George. Can you all see this slide?
Yes, we can.
Hello? You can. Okay, great. Thank you. Thank you. And thank you so much for having me today. Special thanks to you, George, and to your staff, especially Holly and Bethany. They helped me through some panic-inducing moments earlier today. I would like to congratulate Argonne on its 75th anniversary, and thanks to the audience for your interest. I hope everyone is safe and healthy. I know these are very difficult times. George, I live in New Mexico, but I work in Washington. Until COVID, I had been commuting to DC every week. And so I've been in New Mexico longer than I have been since college. I'm also a child of the DOE labs. My father worked at Sandia for 42 years. Both in Livermore and in Albuquerque, starting long before there was a DOE. I'd like to say you all are the technology experts. I ran the DOE policy office in both the Clinton and the Obama administrations. In fact, I'm actually the longest serving political appointee in the Department of Energy's history with almost 12 years. My daddy's still getting his laboratory pension. He's 91. When I was at DOE, I had to recuse myself from lab pension issues, so I could be honest. Again, you're the technology gurus, and I'm going to focus just a little bit on policy and batteries, first in the transportation sector and then on grid scale batteries. Time is very short, so I'm going to talk very fast. This is global EVs and plug-in hybrid EVs needed by 2030 to meet net zero emissions targets by 2070. This is an IEA sustainable development scenario. The light blue, light duty battery electric vehicles, the dark blue, light duty plug-in hybrids, the green is light duty, light commercial electric vehicles, and yellow is buses. Here's millions of vehicles. This is 2019. This is 2030. There are probably 7 million worldwide now. By 2030, there are approximately 5 million light duty vehicles. We're going to need 140 million by 2030 to meet that net zero target by 2070. There are approximately 1 million light duty plug-in hybrids. We're going to need 60 million in 2030. Zero light commercial battery EVs in 2019, we need 30 million in 2030, and there you see zero bus battery electric vehicles. We're going to need 5 million in 2030. That's 229 million new EVs or hybrid EVs in the next 9 years. We all know about Ford and GM commitments, and growth will be exponential. And we still need better technologies for shipping, heavy-duty vehicles, and air travel. In my view, this raises both technology investment issues, work for the labs, as well as supply chain issues. I'm going to say just a little bit about this. This is a supply chain for lithium-ion battery. You can see there, this is the EU, US, and China. Nickel, a lot of it in China. Cobalt, not in China, that's in a Democratic Republic of Congo. A lot of graphite, lithium, and manganese, much more in China than either the EU or the US. Here you're looking at chemical processing and refining. That is a worse story. 93%, the professor mentioned manganese, 93% of that is processed and refined in China. The US and EU do very, very little processing and refining. Manganese, I looked up while we were talking, is in Brazil, India, and Australia. Here you're looking at the cathode and anode production, and again, US and EU, we're both at 0%. China is the major manufacturer of anodes and cathodes. And here is your manufacturing. We're 10%, China 73%, EU 6%, and there's your batteries. A little bit more on where the reserves are of these critical materials, metals and minerals. US has 35, these are in metric tons. US has 35,000 metric tons. Chile, 8 million metric tons. Australia, 2.7 million. That's compared to our 35,000. I know we're looking at the Salton Sea, et cetera, but that's what it looks like right now. Cobalt, we have 38,000 metric tons. That is in the Democratic Republic of China. Professor mentioned that it's being mined by 5-year-olds. That is true, although they have jobs. They would fight back on that. Australia, 1.2 million. Here, nickel, you can vary the nickel and cobalt in a battery. We have 110,000. That's all in Indonesia, 21 million metric tons in Indonesia and 11 million in Brazil. I have some policy recommendations in that regard. We should increase our diplomatic investment focus on Western Hemisphere and Africa, protect the supply chains for metals, minerals needed for wind, solar, and batteries, support new domestic environmentally responsible mining activities. I've been looking at that around the country, increase our capacities and capabilities in key metal chemical processing and refining areas, and promote humane mining conditions around the world. I'm going to switch here from talking about EV batteries to grid scale batteries. We did a study of California about 1.5 years ago. This is every day of the year, actual generation, not modeling or data or anything like that. It's actual data. And the red is solar and the blue is wind. And the numbers you see coming up are the actual days in California in 1 year, 2017, with little to no wind. 90 days, 1/4 of the year with little to no wind, 11 days in a row, 10 days in a row, 5, 7 days in a row with little to no wind in California. This is CalISO actually has requirements for batteries, but right now they have 181 megawatts of battery storage, or this was in 2019, 502 megawatt hours of battery storage. You can see the duration there. There's a little bit of 6, 7, 8 hour storage. I assume that is a pumped hydro. The 4-hour storage there, that's what the duration is of a typical lithium ion battery. Total generation in California in 2019 was 202,000 gigawatt hours, and they have 502 megawatt hours of battery storage and 90 days without wind in 1 year. We were also interested in whether that was an aberration in California. It wasn't. We looked at Texas. They also had 90 days with no wind and different times of the year, but 90 days with no wind. It's a wind capital of the country. Also in 2015, there was prolonged drought in California that reduced hydro from about 21% in 21% to 7%. Okay, so big variations in hydro based on drought. And in 2018, hydro dropped again to about 13% of generation. They also have huge seasonal variation. The difference between wind and solar in the summer and winter is 3.2 terawatt hours. So it's more than just batteries cannot solve that problem. I'm going to skip through this slide. It just takes too long. And the two things I would say about that, only 10 states have grid storage policies and targets. When you, underneath one of the animations, looking at a DOE report, the longest duration storage and the least expensive storage on that DOE report released in December of last year, compressed pumped hydro, obviously, compressed air energy storage and hydrogen storage have the longest duration and are the least expensive. What you're seeing in this one, and this is my last slide, are 10 EIA electricity regions. Can't figure out the rationale for their regions, but you see there the green on the California, Oregon, and Washington. That's one region. And it is an overlay of those regions on top of the National Energy Technology Laboratory's potential sequestration sites. Okay, but it's not just sequestration, it's hydrogen storage, compressed air energy storage, bioenergy with CCS, et cetera, et cetera. What I wanted to do was look at and see the relationships between hydrogen and CCUS and storage in a range of areas. And so you can see here the big beige area is in, say, Montana, North Dakota, South Dakota. That's a big saline formation. The dark red are oil and gas reservoirs, and the black is unminable coal seams. And then these are cement plants, steel plants, refineries, the approximate number of gas processing units, and the approximate number of chemical processing facilities in 2019. And these are those 10 regions looking at their fossil fuel generation, mountain regions 69%, as well as the associated jobs, 258,000, west, north, central 57%, where you all are 65% gas and coal generation, 326,000 jobs associated with that, and so on and so forth around the country. West, south, central is the highest, 71%. Gas and coal generation, but and 1.2 million jobs. And then here, Pacific contiguous, only 30%. That's all gas. They don't have any coal generation. But another problem for them, the other percentage, their large percentage is hydro, and the glaciers are melting in the northwest in Canada. So there's going to be a problem with that in the future. So this is where the cement plants are. This is where the steel plants are. This is where your refineries are. This is the approximate number of gas processing units and their locations. Here's chemical processing facilities, and here's all of them. And when I look at this, and we're talking about storage, hydrogen storage, compressed air storage, CCUS, and the users and consumers of both hydrogen, the producers and consumers of hydrogen, and then cement is kind of out there, different but very important for our economy, and where they are located, you start seeing hubs form up. And I like maps. I think they show strategy. It is our opportunity right now in the clean energy transition to build out shared infrastructures, storage, BECCS, CCUS, hydrogen storage, compressed air storage, and in these locations, and start decarbonizing our economy and moving forward on a clean energy economy. And so thank you very much, and back to you, George.
Thanks so much. It's really a complex challenge that we face, as you pointed out. Well, I think it's time to move into the panel discussion. I would ask all the panelists to unmute their videos and their audios so we can all be together in the same virtual room. We want to talk about the future of the electricity grid and to some extent transportation and the role of storage in shaping it. Might say, as our panelists have pointed out, the grid is changing rapidly on the generation side with wind and solar and the storage needed to firm it up and manage it. Also on the distribution side to work with demand response and managing the peaks that usually come in the evening. Do people turning on all the electricity that they need or if they come home from work. So we would like to ask the three panelists their thoughts on the future of the grid. Can we get to 100% renewable, fully decarbonized grid that serves all customer needs with environmental justice for everyone? What are some of the highest barriers we need to overcome and some of the greatest benefits that we might achieve? We want to take audience questions as well, so please don't forget, audience, to put those questions into the chat. Let's start with Mary. Mary, you brought Green Mountain Power to a model grid of the future in only 10 years. Can your experience be duplicated at the national scale? What do you think? What are some of the challenges?
Yes, I mean, I think absolutely. From my perspective, I think the most important thing to start with is really to start with getting to 100% carbon-free. With the idea that we're using that as a transition to 100% renewable. So there's no mistake to why when we launched our very aggressive goals, it was first around low carbon. So it's about getting to really Green Mountain Power is on the path to be 100% carbon-free by 2025, 100% renewable by 2030. But yes, I absolutely believe it is possible. I feel like it is, yes. So I am all there, I think, as you probably know. So every region has different challenges, but again, from my perspective, the cool thing is technology exists. So it really is, again, I think that combination of, incredible advancements in science along with love of people and the planet, because our focus was always the love of Vermonters and how do we transition as fast as possible in a cost-effective way for them. And I think when that is the lens, it's amazing what people can accomplish, particularly when they bring together those forces.
Yeah, and we do experience now, I think, especially in the last 3 or 4 years, a real public acceptance of the need to go renewable and to decarbonize. And to me, that's one of the biggest changes that we can expect going forward. Melanie, may I ask you, you've seen lots of not only the triumphs but also the challenges of the grid, and you pointed out a few along with a few opportunities. What are the biggest barriers in your sense, or let's say the biggest opportunities?
I think that the biggest opportunity is also a big barrier. And I would like to say that I am not particularly interested in picking technologies. I am actually interested in deep decarbonization. And so I don't think that we should say it should be 100% renewables. When I showed you the 90 days with no wind, our conclusion is for the foreseeable future, you are going to need a fuel. And probably if we had a different grid structure, you would probably need, could use a lot more wind and solar and a lot less fuel. But right now, our grid market structure, basically we designed it in the late 90s, early 2000s, and it is not amenable to a lot of new technologies. But I also think that we are going to need, I think we need to electrify our transportation system. I think it's going to be harder to decarbonize, not decarbonize, we can decarbonize the grid, but I think storage is going to be much more of an issue for the grid. We need to think about other things. But as we increase electrification of both transportation and of buildings, we are going to need to build out our grid. And I see Mary is in Vermont. We did a study of New England. I did a reference frame for New England, replacing the gas, coal, and nuclear with onshore and offshore wind, very space constrained, and it's a reference frame, so it's not reality. But offshore wind, to replace all of that, you would need 2,183 offshore wind turbines. I would just point out how long it took to get Cape Wind moving in New England. And what I'm doing is underscoring a huge problem. We're going to need to electrify a lot more. That means more structure, and everyone is opposed to siting infrastructure. And so I think that that's a huge, huge problem. I have a slide that I show just citing headlines in New England, headlines from actual newspaper headlines opposing any build out of infrastructure. And so I think in order to build out our grid, to increase electrification of both transportation and buildings, quite frankly, we're going to have to do a lot of that. We're going to need substantial build out of the grid, and the public stops it at every turn. And so I think that that's a challenge, but I think that I am inspired by you all technologists. It's the policy people like me who hold everything up. So
interesting perspective.
Yeah.
Let me put a question to everyone, and Stan, feel free to answer this. We haven't asked you yet, but you talked, Melanie, about the need for something to burn and for better storage. Let me ask the panel, can hydrogen fulfill both those needs? It's pretty easy to store hydrogen as long as you like. It, in fact, can be a drop-in fuel or almost a drop-in fuel for natural gas in gas turbines for generating electricity. And, of course, you can use it in fuel cells, as Stan was pointing out, for transportation. Is that a solution that we ought to be pursuing, let's say, much more aggressively than we are? Anybody to answer, please.
Yeah. That's why I showed the slide with the hubs, because I've been looking at, I think we urgently need to decarbonize. Okay, so we need action with technologies that we have now. CCUS is economic if you have an infrastructure, as is hydrogen. And I wanted to see if I could share those infrastructure. Can I get CCUS investments now and repurpose those pipelines for hydrogen in the future? I talked to pipeline experts. They said, absolutely, you can. And so what I'm trying to do there is to show all of the different things you can do with new energy centers focused on electrification, CCUS, and hydrogen as both storage and fuel. But again, I think you can, as you said, you can store it. So I looked at the storage locations as well for the hydrogen and for compressed air storage. So I think we can do it all. It's going to take a lot of policy work. And anyway, that's a few thoughts. Yeah.
Wonderful.
Yeah,
Stan, can I ask Stan, what's your sense of hydrogen?
I think I already mentioned it a little bit. I'm not sure it's so easy to use the present pipelines because they'll get embrittled. You would have to replace them for sure. But I would like to go back to the previous question. Something that has not been mentioned yet is nuclear power. Nuclear will be there as a baseline. New York State's spending tons of money to keep the present plants going. They're green in the sense they don't make CO2. So we have to look at new nuclear options. But the other thing we have to look at is more in Melanie's bailiwick, policy, politics, whatever you want to call it. Texas got themselves in trouble. We don't want to connect to a national grid. Compare Arizona and Hawaii. Every house, every building in Hawaii has solar cells on it. Maybe 1% of the homes in Arizona have solar cells. The sun shines there every day. There's some obviously political or policy reason why it's not a good investment there. And in the end, we need, like other places, we need a national energy policy. So the states can interact, that we can build a grid from state to state. And so if Texas has this problem again, they can import the energy. But it needs to be more top-down and get some of these really impediments out of the way.
There are I'll just comment, lots of studies now that show that the transmission grid nationally has to be built out if we're going to have a renewable grid. And right now, it's 50 silos, each state sort of playing selfish for its own good. And that prevents the transmission grid from growing. Any comments on that? Mary, anyone?
I would love to build on what Stan just said, because going back to the question about hydrogen, I think, yes, hydrogen can play a very important role, but I agree with Stan. It's a lot more complicated than I think a lot of folks are making it sound, because you can't just plug and play with the existing infrastructure. I also agree with what Melanie said about, really banana, which is build absolutely nothing anywhere near me. I mean, that's, so I agree. But I guess the slant I would have that's slightly different, and I also agree with the importance of existing nuclear, to tell you the truth. That was a big part of how we created an affordable path, was leveraging existing nuclear with its, zero carbon or very low carbon output. All of that said, because of all of these factors, I really am a believer, particularly in rural America and rurally around the world, you are going to see an acceleration of an adoption of distributed technologies and less reliance on the grid. And so I think it's going to be the great mystery to see how all of this actually plays out. But I think one of the mistakes, in my view, of what people are thinking, it's that the grid is that we're still going to be using grandpa's grid in the same way 50 years from now. I just don't believe it. I don't believe it. If nothing else, because of the companies I'm involved in, the amount of money I'm seeing going into venture capital on technologies that can self-supply at the business level, the home level, the community level. So I think it's going to be very interesting dichotomy between the larger grid approach for major urban areas and a very different approach for rural America. So, and again, the distributed technologies are only getting cheaper and more reliable, and storage is a huge part of that.
Melanie.
Yeah, I actually totally agree with that it's going to be very different for rural America than it is in urban America. But I've been looking at the world too, and have spent a fair amount of time in Africa and looking at what's happening there. And by 2030, the world is going to add 10 cities of 10 million people or more. 4 of them will be in Africa. Distributed technologies are not going to suffice for cities of 10 million people or more. And so I totally agree on rural America. One other thing, and I'm gonna put in a plug for a professor said we needed a national energy policy. When I was at DOE in the Obama administration, we produced the Quadrennial Energy Review, the one that we put out in 2015, that was rolled out in Philadelphia by Vice President Biden, had a major call-out box about Texas and what happened in Texas in 2011. It had a very, very cold spell, and our concern was the growing interdependencies between gas and electricity, natural gas and electricity infrastructures, and that they needed to be paying a lot more attention to that. I would say that the wind turbines don't freeze in Minnesota. They froze in Texas because they haven't made their grid resilient against cold snaps, but they had one in 2011, and we analyzed it and said you need to do X, Y, and Z. And one other thing, the professor raised the issue of pipes, embrittlement of pipes. My question was new pipes. Okay, if you need new pipes for CCUS, can those be repurposed at some point for hydrogen as we move to a hydrogen economy? The answer was yes. They need to be better than they might otherwise be, but they can be multi-purpose. So that's about new pipes. And how can I incentivize a bunch of industry people to capture and store their carbon when those assets might be stranded in 20 years? And the answer is, can they be repurposed? And the answer was yes, if you do several things right. So, yeah.
There's no doubt that we have a huge opportunity in front of us to do things differently. And pipes and hydrogen and CO2 capturing and reuse are part of it. We have time for maybe one or two more questions. Let me put this one out. If you think of the wildfires in California, the freeze in Texas, and Mary, you were talking about a distributed grid growing, would people with many more, let's say, storage at home have solved some or maybe all of those problems?
I mean, there's absolutely no doubt that if you had massive deployment of storage at home, you would solve a lot of problems. I mean, it was in a small little rural state like Vermont. It was, even when we got up to, oh my gosh, I think it was only like 1,500 homes with storage, we were able to save, easily $1 million on a hot day in terms of, beating down the peak. And the vision was always, how do we, actually get away from 1990s thinking of like beat the peak, attack the peak, and just flatten the sucker. Just have it never, talk about making a grid. Part of the challenges with Grandpa's grid is it's not economically, it just doesn't have good economics. I mean, even on a good day, the grid is like about 45% economically efficient. It's just a very inefficient way to think about delivering energy to cities, to rural parts, to anywhere. So storage really can be the killer app in the context of making it much more flexible. And really, again, our strategy was always a combination of utility scale, customer-based storage, deployed distributed storage, and really getting to the point where there just was nothing that you never were talking about peaks because they just didn't exist anymore. You had a system that could basically flatten it year round. So yes, is it possible to do it tomorrow? Absolutely not. Is it possible with the right policies in place and the right leaders in place to move much more rapidly and make a huge dent in the next kind of Texas-sized event? Absolutely.
So I was reading about people in Texas who happen to have Teslas with batteries that you could access, and they powered their homes for a few days with their Tesla. And their neighbors were coming over to charge all their electronic equipment. So, I mean, here's an example, small scale, but magnify that. And as you said, Mary, get the right policy, get the right incentives, and you could imagine this happening, let's say, in 10 years.
Yes, absolutely.
Well, we're running out of time. I'd like to thank Linda and Paul for kicking off this virtual event, as well as our great speakers, Stan, Mary, Melanie. Really thank you. We appreciate your willingness to bring this topic to life at Argonne. To our audience, thank you for joining us today and for the first installment of the Director's Special Colloquium Series, celebrating Argonne's 75 years of the pivotal science and technology discoveries that accelerate U.S. prosperity and security. We hope that you'll join us throughout the year for additional events. Please visit anl.gov events to learn more. Thank you so much, and everyone, please enjoy the rest of your day.
Thank you.